Right. So yeah, we're going to be talking more about SQL. Uh, so far this week, you guys have learned how to query to write SQL queries against tables that already exist. And starting now and going into the rest of the week, we're going to be focused more on like how you create those tables. Um, so creating those tables is very similar, I think, conceptually to object-oriented design. If you have an application, you have to think about, okay, what kind of, entities or objects do I want to have? And uh, not only what objects do I want to have, but how are they going to be connected? How are they going to interact? What are the relationships among different objects going to be? So I think conceptually it's very similar. All right, so let's take a look at this. And um, so is there, I guess the first question would be like, if you were at a new job and you sat down and you got, let's say, an Excel spreadsheet, and it had a bunch of rows in here, I had a table that looked like this. What kind of application do you think you're looking at?
Like some sort of store that's keeping track of orders.
Okay, cool. Yeah, so a store that has information about orders. So what might you call this if you had to give a name to this table or spreadsheet?
Sales info.
Okay, sales info. Okay, good. Um, so do you see any potential problems with this?
I think that the personal information is not necessarily related to the ordered stuff.
Okay. Yeah, so we have a bunch of, let's say, different information all included uh in the same place. So I think, yeah, this would be the coding equivalent of having one giant function that's, 300 lines long and does 10 different things. So, so one question you could ask is, how could I separate out different entities? So is this really one thing? Do all of these things, does all of this information belong in one table? And if not, what what are the entities here that you could pull out?
The name to birthday could be pulled out
Okay, yeah, from name to birthday. Okay, so why could that be pulled out?
because it's related grouping, so they're related to each other. Like they're information about the customer themselves, and the rest of
Okay,
it is the information about the items.
yeah. So this is really like about a customer. So, if we start with, sales info as a table, well, sales info really contains customer, like at the very least, there's a customer here. So there's an entity that's kind of grouped in with everything else. Are there any other entities that you can see?
The order information. And then I will say it's a bit unclear to me whether the first column ID is referring to the person that put the order or the
Mhm.
order itself.
Yeah, that's a great question. So what do you think this ID column is doing?
It's keeping of it's keeping track of that. That's related to the customer. Like the customer that's their ID.
Okay. Okay. Do you think it's the customer? So if Sally Smith places a new order, so if there were a Sally Smith placed a new order, it would be another row with two Sally Smith, etc.
No, actually, it's the ID of the orders, like how when you like order at a restaurant and they give you like a number, right? Like order number 50. So it's
Mhm.
like keeping track of the orders. Actually, yeah, it makes more sense if that's the case, I think.
Okay. So are there any properties of the ID column? Like, could the ID be anything?
I mean, it really could be anything, honestly.
Okay. So what is the purpose of this ID column?
So you can find based off of, I mean, the order. So find off the ID, you can say, oh, ID 2, Sally ordered a lamp.
Okay, yeah. Yeah, so if we were to continue placing new orders, so what do you think the next time someone places an order, what do you think the order is going to be? The order ID or the ID here?
3.
Yeah, if we, extrapolate out, the next one's probably 3, and then that's going after that 4. So the ID 1, it's incrementing. So each time we have a new entry here, we're going to get a new ID, and that ID should also be unique. So this ID property, this column here, the purpose that it's serving is to uniquely identify each entry here. And then we have the question, if we have a unique identifier, like what is this? So the combination basically of unique properties, which could be either just a single column here or a combination of other columns. That's something called table grain. It basically answers the question like what does a row represent? What does it mean? Okay. And then if we look at some of this other information, is there any redundant information? Do we need all of this information?
On first glance, it feels like the age and birthday might not feel that important.
Okay. Okay, so age and birthday, yeah. So what do you mean by not important?
So for instance, if this were an app related to a grocery store where maybe they sell something like alcohol, I could think it would be more important in that context, but in this
Yeah.
context, the items that seem to be sold here, maybe it doesn't really matter.
Okay, yeah, so that's definitely a good thing to think about. So for the purposes of this application, do we actually need, what information do we actually need? So what does a user actually have to keep track of that's meaningful for this application? So let's just say hypothetically that, this application, when you're 65, you get a 10% senior discount or something like that. So let's just say that this information actually is useful to the entire application. Do we need both of these fields?
You don't need age, you could just get it from birthday when you need it.
Yeah. So basically we can derive the age column from the birthday. And you know, this is just birth year, but you know, you could imagine a full date. So this is a simplified example, but in general, you can derive the age from the birthday, or you could also go in the reverse direction, potentially. But yeah, so if you have their birthday, then you can get their age. So when you're thinking about, you know, database design, you should also try to imagine, just like when you're writing a function, scale it up to 1 billion. So now this table has 1 billion entries. We have 1 billion entries, and now we're storing redundant information. So that adds up to, you know, performance issues and cost, you know, cost money to store information. And when you scale up, you don't want to be storing information that you don't actually need. Is there any other redundant information here? Or information basically where a column could be derived from other columns?
Order total.
Yeah. Yeah, so ordered total looks like it's basically the number of items multiplied by the item cost. So I think this is another example of a column which is based on derived information from other columns. So in that case, this is basically redundant, and so we should avoid it. So there are ways. So there's a link. Yeah, there's a link here if you are interested. Something called database normalization. And this gets kind of academic. I wouldn't worry above the third normal form, but so if you're taking like a computer science course, you'll get exposed to this kind of thing. But basically, it's how do we pull out entities and how do we reduce redundancies? Okay, so let's say that we decide, okay, we have a customer entity and that we have an order entity, and we can, you know, remove the age column and the order total column. So that's a good initial step. The next question to think about is what if things change? What if data changes or we make updates? So what if Sally Smith moves? So if Sally Smith, you know, has been a long time customer for years and she's got lots of different orders, and then at some point she moves. Well, then we have this issue where, you know, we potentially have to update her address, or if she changes her name, do we have to update her name everywhere? We now basically have two different versions of this customer entity, and they're all kind of mixed together. So that creates issues with data consistency and integrity. So that's another thing that we have to think about. So that's one reason to pull out, for example, certain entities. All right, so I think we have a good general picture of how we could improve this, at least some initial steps in that direction. So let's go ahead and try and implement that. So before we implement it, I would basically, strongly encourage something like insist that you draw it out before you start actually writing SQL to implement it. So I'm going to go here. I'll use Excalidraw. There are a number of other tools you can use. I think you've probably been exposed to some of them already, but I'm just going to use this. So we need first to decide what our entities are. So we have customer and order. So we'll go ahead and create those. So we have a customer, and what fields does a customer need to have? Well, let's just say for now, name, address, and birthday. The birth year. Okay, and then we have an order, which is going to have the item, let's say item amount. Let's see. And item cost. Okay, so we have these two entities now. And if we look at customer, are there any other entities in customer that we might want to pull out? And when you're asking this question, you're basically asking, is something simple actually complex? So are there any fields here that are actually complex?
Filled.
Sorry?
The address.
Yeah. So the address, we could, store this as right here, just one big string here. But this actually has multiple components that each have their own meaning. And so if we store this just as one big string here, it gets a little harder to validate. Someone might enter their address differently one time, so there's all kinds of issues there. So it might make sense to pull out address as its own entity. You can go ahead and do that. And then an address, just to keep it simple, let's say street and city. So we could obviously, keep going. An address could be much more complicated, but this is just a representation. And even name, right? Name is also potentially a complex object. You have a first name, you have a last name, you have a middle name, maybe a title, maybe you have two middle names, so there's all kinds of complicated things that could be happening there, but we'll ignore that for now. Okay, so now we have three entities. The next question to ask is, how are they connected? So for example, a customer in an address. So how are these two entities connected?
You mean currently or?
I mean, in principle. So let's say, we have an e-commerce website or something like that. So we need to, deliver whatever they order to their address. So there are a couple, there are basically three types of relationships you can have in a database. The first one is one-to-one. The second one is one to many. And the third one is many to many.
So in this case, it'd be 1-to-1, right? So a customer has a address.
It could potentially be one to one. It's a little tricky because that would mean that customers, for example, couldn't share an address. So if one address belongs to only one customer.
So
One
many
to
to
many.
many.
Many to one.
Yeah, so all three of those answers are possibly correct. And how do you know that it's correct? Well, you have to think about your application. So yeah, this stuff is a little tricky. It can be very flexible. So it depends on exactly what your application is doing. So for example, in my Amazon account, I've moved a bunch of times and they have all my other addresses. So in that case, and then my wife lives at the same address as me, so she has the same address. So in that case, it is a many to many relationship because lots of customers could potentially live at the same address, and then customers could also potentially have many addresses. To keep things a little simpler, so most of the time your relationships are going to be one to many. So if the relationship were one to many, then we would say that a customer has one address, but an address can be associated with any number of other customers. So again, if you live in an apartment with three other guys, all three of you could have the same address. Okay, so I'll just draw an arrow, and then the question is, we'll get to this in a little bit, but how do I actually connect? So let's say we've decided that customer and address have a one to many relationship, but how do we actually encode that?
You can do it by IDs.
Yeah. So one thing we would probably want to do is make sure that every table we have, every entity has essentially a unique identifier. So in this case, we could just give that an ID. We could also give this an ID. So it's also potentially the case that a customer, like multiple customers, could have the same name and birth year, right? So that might not be sufficient to uniquely identify a customer. So we can create a key here. So there also, there's synthetic keys and basically natural keys, and you can also use different combinations to create a unique value. But just for the sake of simplicity, we're just going to use ID for everything. Okay, so now customer has an ID and address has an ID, but a customer needs to have an address. So how do I connect those? You basically are going to have to create a link between an address ID and a customer is going to have an address ID. So address ID, and this field is actually just going to point to this ID. So I can draw this line. So this is going to point to this ID field. So you have a customer, and the address ID is just going to be a reference to this. So this is how we can have complex entities and still show those relationships. So we don't have to literally include all of the information in an address inside the customer. We can just pass it a reference. Okay, And what about a customer and an order?
The order would have a customer ID. So the what do you call it? Order ID is pointing towards the customer, or there's like a customer ID field
Yeah,
in the order.
right. Yeah. So if we have a specific order, again, depending on your application, you could potentially have multiple customers have the same order, like if you're splitting the check at a restaurant or something like that. But in our case, we're just going to say that that's not how it works. So an order has to belong to exactly one customer. So in that case, order needs a reference to the customer to which the order belongs. So we can add another field here and call it customer ID, which is similarly going to be just a reference to this. So this is basically how we express those relationships. We'll see next week. We'll learn how to handle many to many. It's a little bit different, but you know, one to many relationships are fairly straightforward like this, where you decide what your entities are. You decide basically what makes a given instance of this entity unique. In this case, we're just using an ID field. And then we decide how they're connected. And so the thing that owns the other thing gets a reference to the other table. Are there any questions about that?
There is no such thing as a table property being something like a list or an array, right? So instead you would have multiple rows, for instance, under the table order that all point to the same customer, but you wouldn't have a field under customer that has like an array of orders or something like this, right?
Yeah, so that's a great question. And that's basically what you intuitively want to do, right? So if a customer has a bunch of orders, then like, well, we know how to do that, right? We have lists and arrays. And so we just, you know, anytime a customer creates a new order, well, we just append, we could just append that the order ID to the customer or whatever. And you definitely can store arrays in databases, but you should, for purposes of this course, you should pretend that arrays do not exist in the database. Yeah, so the way this works is you would just have several, if the same customer creates multiple orders, you would just have several rows in the order table, each having that same customer ID. So that way, you can actually create lots of orders, but only have one instance of that customer. So you don't have to. So for example, here, every time there's an order, well, we have to save all of this customer information over and over and over again for every order. Whereas when you do it like this, you just have one customer. So it's one customer, it's easy to keep track of, it's easy to make sure that, things are up to date and so forth. All right. So why don't we take we'll take a 5-minute break or so. We'll come back and then we'll see how we can actually implement this in SQL. Okay. So we'll go back to today. and we have our diagram. Okay, so we've basically like planned everything out. What does our application need to do? What information does it need? We pull out these entities. We determine basically the properties of each of these entities, the columns that they need to have. And then we figure out how they need to be connected. So what are the relationships between these entities? Okay, and once we have that diagrammed out, we have to actually implement this in SQL. So what I'm going to do is I'm going to use Docker, and I'm going to create a Postgres database. So we go here. I'll go grab the official image from Postgres, and I'm going to scroll down in the README, and here's like a very basic default command that I can run to get a Postgres container up. So I'm just going to copy that, and I'm going to go to my command line, and I'm going to run this. Okay, so I have something left over. So Docker images. Okay, Docker PS, Docker. So nothing is currently running. So I'm going to check basically old instances. So Docker PS-A, and I'm going to remove this. So Docker RM52. Then I'm going to try to run this command again. And I get the feedback. So this is running. So what does this -D flag do?
I think it's that.
It's for database, right?
Okay. This is a Docker command. So Docker itself doesn't really know about databases. So it happens to be a container that has a database, but Docker doesn't know that. But that's a good guess. So the -D is actually for daemon mode. So running it in the background. So you can see what happens if I. So let me just try quickly running it. So Docker stop to F, Docker RM to F. Okay, so I'm gonna run this command, but without -D. Right, so now if I run it without -D, my terminal is basically connected here. So if I want to do something, I, create a new shell and then do stuff in there. So -D is basically run it in the background as a background process. We're in daemon mode. Okay, so I'm going to run the original command. I'll run it in the background. Okay, so I'm running this in the background. The problem is I now want to connect to it. So I want to connect to it from the front end. And because I don't have any port forwarding, there isn't a direct way for me on my host machine to actually connect to this database. So in order to do that, I'm going to add an additional flag here to do port forwarding. So by default, Postgres will run on port 5432. And Postgres is in fact running. If I do Docker PS, this is actually running, and it's running internally on port 5432, but I don't have direct access to that from my machine. So I need to create a connection between my local machine, my host machine, and then the container. So I'm going to stop this again, Docker stop 61, Docker RM 61. I'm going to do port forwarding. So -P, and then I can pick an arbitrary port on my machine, probably best to avoid 5432 in case you have local Postgres running. So I'm going to pick 5454 for no real reason. And then the internal port that I want to map to is the default 5432. So now I can run this and nothing looks different. But if I do docker ps, I can see in the ports. Now before it was just showing me the internal port. Now it's showing me that from my local host 5454, I can now connect to the Postgres server inside the container. All right, so how am I going to do that? Well, we saw last week from the cars database. So there are ways to do it from the command line. It's kind of like a low level interface. But for the sake of convenience, you can also use another tool. And there's one called dbeaver, which is free and works with all kinds of different databases. So I'm going to use this, but there are other things available as well. Give that a second. Okay, so this spins up, and what I want to do now is basically create a connection to that Dockerized Postgres database. So I'm going to go here, and this is just specific to dbeaver, but any other tool you use will be similar if you want to use a tool. So Postgres, right here, I'm going to create a connection, a new connection to Postgres database, and then I have to configure it. So there's a couple fields I have to figure out. The host is localhost, so that's fine. The port, however, is not going to be 5432 because that's what's running inside the container. So I need, since dbeaver is running on the host machine, I need it to use the 5454 port. And then the username is Postgres, so that's the default, that's fine. And then the password, I'm gonna have to get from here. So when you run this, the Postgres, this Postgres image is set up in a certain way to accept certain parameters. It's a little arbitrary, but at the very least, you have to provide a password. And this -e is an environment variable. So we're running the image and we're passing the container an environment variable, and then the container will pick up that environment variable and configure the database to have this password. So I'm going to copy that password, and I'm going to paste it in here. And now I'm going to click on test connection. Okay, and it can actually connect. And if you have problems with that, then you'll have to play around. Maybe your password is wrong, maybe your host is wrong, maybe your port is wrong. But in this case, everything is working, and I'll click finish. So now I have a connection. This GUI interface has a connection to the database. So I want to actually write some SQL in a convenient way. I'm going to open SQL script here. So now any SQL I write is basically going to get executed on this in this Postgres database inside of the container. All right, so what do we want to do? Well, we want to implement this. So the order in which we do things does matter. So for example, if I created a customer first, so if I created a customer table and I said it has a connection, it has an address ID which is connected to an address table, and this table doesn't exist, then I'm going to get an error. So there are a couple ways around this, but I'm just going to show you the simplest thing. So the first thing you should do is determine which table doesn't depend on any other tables. And in this case, it's the address. So I'm going to create an address table. So the syntax for that is pretty sensible. Create table. And conventionally, SQL commands are in all caps, but that's actually not enforced. So out of laziness, I'm not going to use all caps. So we have create table, and then we can pass it a table name. So in this case, we'll call it address. And then we have to specify the fields that it needs. So this is just like in Python, if we're creating a class, we have an init method, and then we specify the properties that it has to have, self.name, self.whatever. So in this case, we need to have an ID. And Postgres has a convenient thing for us that will automatically handle auto incrementing in ID. So if we have this field right here, the ID field, and we can imagine, the next one will be 3, the next one will be 4, et cetera, et cetera, et cetera. But if we had to manage that ourselves, you can imagine it getting kind of messy, because now your application somewhere has to keep track of the IDs in the database and so on. Do you guys experience this problem when on the last assessment, or the last assessment where you had to implement the Blockbuster video store rental thing? So you basically have to query the database to get the current biggest ID, and then you use that when you save it. But if you think about this happening at scale, you can get race conditions where if you have millions of users all updating and creating rows in the database, the time lag between requesting the current highest ID and then sending that back, and then sending that information back again, someone else could have updated that information. So then you have duplicate IDs or whatever. So it's a mess. So it's best to let Postgres handle that. And you can do that by telling it serial primary key. So this is just stuff you would have to look up. So I'll do that. Postgres primary key. So right here, the primary key is a column or group of columns used to uniquely identify a row in a table, which we've seen. So I'll click right here. And it tells you, here's an example, create table, which we just saw, the table name, and then whatever it is. In this case, we're using an integer. So serial will be an integer. And then we specify that it's a primary key. So I'll look up Postgres. Yeah. Primary key auto increment or serial or something like that. If you're looking for this. See what this one says. Yeah, we have to worry about big serial. Okay, that's a little more complicated than we want to get into. Yeah, this Postgres SQL tutorial I think is probably the best simple source. So serial. So serial is actually a function which you don't need to worry about, but it's going to end up being an integer, and Postgres will manage it. Okay, so we have our ID, and the next thing we need is street and city. We go back here. So what data type should street be? Any thoughts? So let's look in the official documentation here. So when you create tables, unlike Python or JavaScript, which doesn't care about types. It's, dynamically, it's got dynamic typing. Postgres actually does care. So you have to tell it what kind of type the information needs to be when you define the column. There's a whole bunch of different types. Here are some: big int, big serial, bit, blah, blah, blah. So there's a whole bunch of stuff. Mostly we're going to be using so there's character varying. An alias for this is varchar, and this is just a variable length character string. So you can specify a maximum, but we're not going to worry about that right now. So we can use varchar to tell Postgres, hey, this is going to be a string, basically. And then city. Okay, so now I can execute this. So you can either run the entire script in this particular tool, or you can highlight the portion you want to run and then run just that. So I'm going to click that. And when I run this, I get some output. Basically, I didn't get an error, so I can assume that it worked. And then how would I actually check to see if that worked? How would I check to see if this table exists?
You can go into the database and do a select or a /DT.
Yeah, so yes, so if I were connected to the PSQL terminal, I could do that. I can also, since I'm using this GUI, I could do select star from address. And if I execute this, I don't get an error. So if I tried to do select star from, and I run that, I get an error. So relation non-existent does not exist. So a relation is just another term for a table. So address, so I can be sure that this does in fact exist, and I can see the columns here. So there's no data, we haven't inserted any data, but this works. All right, so now what I'm gonna do is I'm gonna go back to my diagram and then just kind of mechanically create the rest of these tables. So what's the next table that I can create that, yeah.
Customer.
Yes, yeah. So I can create customer because customer depends on address. If I try to create order, order depends on customer, which doesn't exist yet. So I'll create a customer. So that's name, birth year, address ID. So create table customer. And this is going to have an ID, just like all of them. So you can just include this by default everywhere. So ID serial primary key. And then customer is going to have let's say a name. And that what type would a name be? We'll say it's varchar. It's also going to have, let's say, birth year. So what type should that be?
Date.
It could be, yeah. So there are date fields. So we could actually pass a date. So there's a calendar date. There's also date time. So there's, a bunch of, specific kinds of things. But let's just say that we only want the year. So there's also an integer. So yeah, I'm just trying to keep this, as simple as possible for now. But so we'll use integer. And then we also need an address ID, right? So how are we going to do that? So address ID. So this yeah, but go ahead.
Oh, sorry, I thought you wanted us to answer.
Go for it. Yeah, if you know, go for it.
It's a integer that references address ID.
Exactly, yeah. So so looking at the diagram, we know that sorry, this customer address ID, it references this, so it has to be the same type. So whatever ID is, address ID has to be that same type, and serial will implicitly create integer for us, so we can specify integer. And then we'll look at the documentation. So, how would you go about doing this? Postgres create primary key. Oh, not primary key. So this is actually called a foreign key. So I'm going to go here. So we have foreign key, blah, 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 reference. So there's a couple ways that you can do this, but you can do that here. So we need to say references and then whatever the table is, and then the column. So you can do address ID, integer, references, and we need address. Then we pass in the column that it's connected to, which is ID. Okay, so now I'm gonna run this and see if it works. So I have an issue.
You're missing a comma after name.
Yeah, yes. So Postgres errors are terrible. They, most of the time will kind of point you in the vague direction. So all this says is there's a syntax error at or near create, which is not real helpful. There's a couple issues. One is that if you're doing multi-line stuff, you have to include a semicolon here. That's why this error is getting called here, but there's also a missing comma right here. So I'll run it like this first. And we get a new error. Address, relation address already exists. So we're trying to create this table, but we already created it before. So we're trying to recreate it, and that's throwing an error. So we're not allowed to do that exactly. So a couple things that I could do. One is I could drop the table. So the command to drop or remove, delete a table. So I could do drop table address and execute that. And now if I try to run this again, I get another error, which is right here. So it's telling me that there's a syntax error at or near birth year. So it's just a comma, the error kind of points you in the general right direction. So if I run this again, this works. So I'm going to try select star from customer. I can see that that table exists, and I can do the same thing for address. By the way, the shortcut that I'm using, in case you're using dbeaver, is Control Enter. So that allows me to run without clicking that. Okay. So this works. So now let's move on to the next one. So we have this order. So order requires a customer to exist. So now we are able to create an order. So order is a reserved word in SQL. So we'll avoid that. Create table, we'll call it store order. And we're gonna first off do ID serial primary key. And then maybe I'll simplify this a little bit. Let's say item and cost. Okay, so we have item. So we'll say this is a var car. And this will cost. And then we can look for data types in Postgres documentation. We could potentially use float or something. There's actually a money type in Postgres, so we'll just use that. Okay. And then the last thing we have to do is an order has to be connected to customer. So we need a customer ID, and that is going to be an integer because the key that it needs to be connected to is also an integer. References customer ID. All right, so now I'm gonna. So I have this problem again. So if you're repeatedly running this, this can be kind of annoying. And then I'd have to drop the table and rerun it. So you can also add another statement here. You can do create table if not exists. I think that's the right table. Or right. Same here. So you can, if you get tired of redoing it, you can include this. You could also just create at the top of the file, you could create some statements that will drop all the tables. That might actually be better to do if you're testing, like adding data and then removing it and blah blah blah. You can just drop the tables at the top every time you run it. Okay, so we should have these tables created. And so I'm going to do select star from store order. Okay, so that exists. I'm going to assume the other ones exist too. All right, so once we have, we've now created our database and we have our tables defined. So everything is set up the way we want it to. So now we can insert actual data. And in the real world and the world of web apps, which we'll be seeing shortly, this information is going to come from your application. So anytime someone, let's say, signs up or creates an account, they're going to make an HTTP request to your API. Your API is going to parse through that request and then basically create a connection to a SQL database like this, and then execute an insert statement. So for now, we're just going to do this by hand, but ultimately, this whole process will be automated. So you'll write Python code that will actually do this. Okay, so let's do insert into address. In the fields, we want our street and city. So we don't want ID because that's going to be handled automatically. Then I can do values. I'm going to do this on multiple lines. Okay. So I'll just make up a street name. So I almost did double quotes there, which I do all the time. So you need to use single quotes for strings in Postgres. So 1, 2, 3, main. I did it again. And I'll do one more. 2, 3, 4, Mm. Mm. Okay. So I'm going to go ahead and execute this statement. And to check that it works, I can do select star from address. And I can see that that data exists. So I'm going to create some more data. So insert into customer, and we want to do name, birth year, and address ID, values, and here we're going to actually give the data. So Bob, birth year, what type is that? Integer. So let's say 1972. And what else we got? The address ID. So let's say he lives at address ID 1. Same thing. Got Sally. Birth date is on 1983. Let's say she lives at 2. All right, and I'm gonna do the last one. So store order. So insert into store order. What columns do we want? Item, cost, and customer ID. So the item, let's just say lamp, and the cost, this is money, so I think we can just use a float. We'll see if this actually works. So 1999. And then the customer ID, let's say 1. So Bob bought a lamp. And then the next one, the coffee maker, and that is 23.9. And Sally ordered that. Okay. Yeah, we can do a couple more, but I think this is probably okay for now. So I already inserted this one, so I'm going to go ahead and insert the other two. All right, so let's make sure this all worked. So I'm going to do select star from store order. All right, so question is, so the nice thing about the original implementation, this like naive implementation, is that everything was there, right? Everything is in one table. You just say, select star from whatever, and you see everything. Here, we've broken it up and we followed, best practices, which is great. So now we're getting some benefits, but the downside is that now retrieving this information is more complicated. So how can I get all of the information about Sally and her orders?
You can join the tables together.
Yep, yeah. So we have to join. So we kind of decomposed everything when we created the tables, and then when we actually want to retrieve the information, we have to recompose it. And you do that with joins. All right, so can you help me out writing the query? So I just want to get everything about Sally and her orders.
So you could do a join, or that statement was fine, but then
Okay.
you could then do a join customer.
Oops. I don't know why it's trying to autocorrect that. Store order join customer.
On customer ID.
Yeah, so we can, just to make things easier, we can always reference our diagram. So we started with order or customer order, give a different name, but you know, if we want to get the customer, we want to connect to the customer now, we have to join on these two.
Right.
Okay, so
So just for so I guess you could do store order dot customer ID.
okay, yeah, store order dot customer ID.
Is equal to customer dot ID.
Customer dot ID. So let's just run this first, and we'll see if it works. So looks like that works. We have the ID, lamp, et cetera, and then we have the customer ID. And notice here is the join condition. So these are the same. This is customer ID, and well, this is store order dot customer ID, and this is customer dot ID. Okay, so now we have this address ID, but we want to now connect the address ID table. So attach this to the end right here.
So then it would be join address on customer dot address ID.
Okay. And again, like referencing the diagram is always going to make your life easier. So address ID connects customer.address ID connects to address.id. It's a little confusing because there's lots of IDs floating around, but use the diagrams, it will make it easier. All right, and then this connects to address.id. So if we run this again, now we have everything. So this address ID from customer is now connected to, we joined this table here. So this is the actual address table. It's all just combined. We basically we've connected 3 tables. Okay. Someone else. So I have all the information from all the customers, but I just want Sally.
You could add another line that says where I think it would be customer.name
Okay.
equals Sally.
Okay. So I'm going to do it like this.
Oh, with not with the double quotes.
Yeah, exactly. So this is wrong, but we'll see what happens. What's the error message? Column Sally does not exist. Not the best error message, but so double quotes are basically used to indicate columns or other. You can like override if you're using like a keyword, you can use quotes to override it. But yeah, strings are single quotes. So we do this. Now we have just Sally's stuff. All right, so that's the basic idea. You create the tables. You have to define the types.
Look at the heart I made with my.
So cool. Give me 1 sec. So yeah, so we have the tables with the types, and then we specify how they're connected right here. So using references, and the reference has to refer, basically, in order to be sensible, it has to refer to some unique field, which we get with the ID serial primary key. And then inserting stuff. And then querying. So that's basically it. So if I tried to now like run this entire script, this, it's gonna, so because of how I set it up, it's gonna create the table if it doesn't exist. So it's actually gonna ignore these three statements because those tables already exist. But it is going to reinsert these values. And then for the query, now Sally has two, it's all the same information, but notice that the IDs are different. The IDs are different because Postgres automatically updated the IDs. So another thing you could do here is if you want to, like, you know, experiment and run things over and over again, you can do drop table if exists, address, drop table if exists, customer, drop table if exists, store. And now if I run this, okay, good. So another error. The error this time is cannot drop table address because other objects depend on it. So if we look at our diagram, I'm trying to drop address, but what happens to customer if address is gone now? It's now got a reference to something that doesn't exist, which is, you know, you can do, but it's a bit odd. So you can add actually a cascade. There's another keyword you can add, basically says drop this and drop anything that it depends on. I think the cascade comes after. Okay. And we can see the query here. Now there's just one, and I can run this over and over and over again, and it should give you the same stuff every time. So now this is, does anyone know what the general term is for an operation which, no matter how many times you execute it, produces the same result? It's idempotent. So you might see that. Basically means, yeah, basically means you can execute the same thing over and over again. So if the way I had it before, it was not idempotent, which means that every time I executed it, I was getting new entries. But anytime I execute this script, it should give me the same result every time. Okay, any questions about this? I'd strongly encourage you to lean on the diagrams. It's much easier to keep track of things.
Is it terrible if a field data type changes down the road?
It's not terrible, so you can definitely update. So let's say, you know, I'm not just running this as a script that I can continually update, but I've run this, it's now in production, it's been in production for a year, and now all of a sudden I'm like, oh, you know what? You know, address birth year, it actually needs to be a date field and not an integer. So you can update fields. So depending on what's already the data that's already exists, you may not be able to do a simple like cast. If you can, then it's pretty straightforward. Otherwise, you have to do something a little more complicated. But yeah, you can definitely update. You can add columns. You can remove columns. You can change the type of a column, even after you've already created it.
Okay, thanks.
Okay. All right. So the challenge for today is going to be to design Craigslist. So I would suggest, do a first pass where you keep it simple. Yeah, that'll be. If you have a question, I don't know if you are muted, so I don't know.
Yeah, I have a question. I was looking for my mouse. So you under the one of the table that you created, you specify cost and money, and running the query, it shows a dollar sign. So what if I'm working with maybe a data from maybe United Kingdom working with pounds?
Yeah.
Well, how do I specify that?
Yeah, that's a good question. I'm not exactly sure off the top of my head. There's one thing that might be the case is you can set the localization of your database. So let me just look it up and see if I can find it. Postgres money type. Let's see. Money type stores a currency amount with a fixed fractional precision. Yeah, so it depends on the locale. So this is a setting you can change in the database, but non-quoted. Well, yeah, so it looks like if you wanted to display this information to a user, you should just be able to store it that way, and then you could do something where you do some regex and replace the dollar sign with the whatever the currency sign is.
Okay.
So I think it's basically just a float that only goes that only has 2 decimal places. So that's what it looks like. Yeah. We'll just see. Yeah, is there a nice way to specify pound when casting the money? Yeah, so someone's comment says basically don't use this for internationalization, but it looks like, yeah. So this is the localization that I mentioned, but there's a configuration. So this is a little more advanced, but yeah, looks like you can update the Postgres configuration. And then, so this, in the case of this, is euros, but
Oh, okay. That makes sense.
yeah, I don't think the dollar sign is not really directly meaningful. So you should be able to store it, and then like at the presentation layer, you could either just use regex to replace the dollar sign with whatever you want, or you can set this configuration to whatever is appropriate. But yeah, that's more advanced, so I wouldn't worry about that in general. Okay, so yeah, the challenge for today is you're gonna have to Dockerize it. So you're gonna follow the same pattern as the cars database. So you can look in here and see how this works, and then kind of use it as a model for doing yours. But you're gonna design Craigslist. Okie doke. Any questions about that?